Now, starting with training, let's take a look at training and its complexities. I already mentioned that training is billions of trillions of operations. The more data you have, the larger the model that you use, the more accurate the results will be. Jeff Dean's presentation, Jeff Dean at Google, he's their chief engineer, said that more data plus bigger models plus more computation will lead to better results of deep learning. And that's pretty fundamental to training. And if you take a look at some of the trends in the last couple of years, Microsoft's recent image recognition network called ResNet was introduced in the year 2015. If you compare that to AlexNet, AlexNet had 8 layers. This deep learning network had 8 layers. Its processing, combined processing inside that network is 1.4 billion operations per second. And it achieved an error rate, meaning that how often it was wrong, 16%. Okay? So 8 layers, 1.4 gigaflops, the total mathematics in the network, and it was able to achieve an error rate of 16%. What that basically says is this. If you have and that was the best in the world. If you have a computer vision algorithm that was written by computer vision experts, most of the error rates are much worse than 16%. And so that tells you about the limits of using computer vision for applications like self-driving cars. Using traditional computer vision approaches, the limits by which you could achieve accuracy is surely limited to something that is unacceptable for all of us from a perspective of safety. However, using deep learning, in the last several years, we've been able to achieve an error rate of just 3.5%. 3.5% tested among millions of images. 152 layers. 8 only a few years ago, 152 layers today, and a total computational capacity of that network of 22 billion floating point operations per second, an increase of 16 times. This states the deep learning problem. In just literally 3 years' time, the computational load of deep learning has grown 16 times. Much, much faster than Moore's Law. The problem is getting harder and harder, and yet computational capability is not growing as fast. That's one of the reasons why the entire industry has looked for a new computing model, and that's why they've all reached out to GPU computing. This is for image recognition, an increase of 16 times in just 3 years. This is staggering here. This is voice recognition. As you understand, voice recognition is the foundation of natural language understanding. And natural language understanding is the foundation of intelligence. If we can teach a computer to understand, not just recognize, to understand the meaning of our words, that computer will be able to learn by itself, by reading books, by going to the library, the world's libraries, and just simply read every single book as fast as you know how fast a computer can work, and learn and get smarter all the time. Natural language understanding is one of the most important areas of research in AI, and voice recognition is at the foundation of it. Baidu's work, this is the work that is done by Andrew Ng and his lab, Deep Speech 1 in the year 2014 had 25 million parameters inside that model. It was trained on 7,000 hours of speech, and it achieved an error rate of 8%, which means that every 10 words was a mistake. 1 out of every 10 words, 1 out of every 12 words. In 2015, by training it with nearly twice as much data and creating a network, a deep learning network that is 4 times larger, twice as much data, 4 times as much parameters inside, 4 times as much complexity. It was able to achieve an error rate of 5%. In just 1 year, Baidu's Deep Speech 2 reduced the error rate by 40% in just 1 year. However, the price to pay was the amount of computation, 20 exaflops. 20 million billion floating point operations was necessary to train this network. As you could see, the amount of computation is precisely the reason why this unreasonably effective approach called deep learning has taken so long to emerge. Until GPU deep learning came along, until the big bang of AI came along, this approach would have been computationally prohibitive. No computers in the world could have trained these networks until the GPU came along. And that's one of the reasons why we're all so excited about this new computing model and why this moment in time in the computer industry is so vitally important. Also recognizing that this trend will likely continue. Remember,